So we're going to look at mixtures, solutions. Solutions are, of course, homogeneous mixtures. We can think of solutions in terms of chemical properties and physical properties. Chemical properties dictated by the solute. In fact, if you pick a solvent that's going to react with part of your reaction, unless it's intentional, it's going to be a mess up. So you usually want an inert solvent. However, the physical properties are going to be much closer to those of the solvent, because almost by definition you got more of the solvent than anything else. So when you're talking about physical properties of a solution, you compare to those of the solvent. There are certain physical properties that will change depending on the concentration. These are called colligative properties, and there's a lab associated with this. Ideally, we do the lab right after this lecture. In 2018, we've done the lab before the lecture, but hopefully all of you in 2018 are listening to this movie before you go into the lab. Anyway, there are 4 colligative properties. First one, vapor pressure, you've actually studied before in Structure and Bonding 1 when you talked about Raoult's law, and I'll quickly refresh you on that. Boiling point and freezing point are the subjects of the lab. Boiling point of a solution generally is higher than that of the pure solvent. Freezing point is lower than that of the solvent. And then osmotic pressure, not so important for chemistry other than determining molar mass of large molecules. Very important, of course, in biological systems. I'm going to have a quick check, see how insane this particular sound is, and then I'll be back for slide 2. Anyway, quickly going through vapor pressure. If you have 2 components of a mixture A and B, well then the vapor pressure comes from both, as long as both are volatile. So for example, if you have component A, the vapor pressure of A is equal to the mole fraction of A multiplied by what the pressure would have been if A was pure. And then of course B, the same thing. And according to, this is Raoult's law, according to Raoult's law, well then the total vapor pressure, which is the pressure according to A, but plus the pressure according to B, is going to be totally related to the mole fraction. So it's a pretty little picture in your book, page 793 in the 3rd edition, that shows this. When you have pure B, so mole fraction B is 1, that's the pressure of B. Here's where you have pressure of mole fraction of A is 1, in other words pure A. Then you can see, according to Raoult's law, B should decrease nice and linearly with the mole fraction. A should increase nice and linear with the mole fractions. You go from pure A, or pure B, excuse me, to pure A, and then the total is a nice straight line that way. Okay, so this is the ideal situation of Raoult's law, where both A and B are volatile. Sometimes you'll get this situation in which the pressure is higher than it should be. This is a situation in which the molecules A and B can vaporize more easily. In other words, they're not held together to the same extent that they were in the pure solvent. So this is where making the mixture disrupts the interparticle forces. Maybe you have a polar substance mixed with a non-polar substance. Maybe you have something that hydrogen bonds with itself mixed with something to which it cannot hydrogen bond, and so on. Okay. Other possibility is, of course, where the total pressure is less than it should be. In other words, the vapor pressures of the components are smaller than they should be. In other words, it's harder for them to leave the liquid phase. And this is in cases in which the intermolecular forces are actually better in the solution. Maybe a solute that couldn't hydrogen bond to itself can hydrogen bond with the solvent, and so you get increased intermolecular forces, so lower vapor pressure. So anyway, you studied that in Structure and Bonding 1, no big deal. We're actually much more interested here, and the rest of this discussion is going to be on this, when the solute is non-volatile. In other words, when you take a regular solid, for example, and dissolve it up in the liquid is going to be volatile. the solid is going to be non-volatile. Now in that case, of course, you don't talk about the vapor pressure of one of the components, you just talk about the vapor pressure of the solvent in the mixture. Okay, so the vapor pressure of the solvent is the mole fraction of the solvent, which by definition will be less than 1 times the vapor pressure of the pure solvent. In other words, the vapor pressure of the solution, when you have a non-volatile solute, is less than the vapor pressure of the pure solvent. And the simplistic reason for that is simply that the particles of the solute that can't evaporate, they'll still be spending some time on the surface, and the time they spend on the surface is surface space that the solvent cannot evaporate from. So essentially, the solute particles get in the way. Quick example, calculate the vapor pressure of 25 Celsius of an aqueous solution of glucose in which 18 grams of glucose were dissolved in 180 grams of water. And I tell you that the vapor pressure of water, so vapor pressure of pure solvent at 25 Celsius is 24 millimeters of mercury. So anyway, vapor pressure of the solution is going to be vapor pressure of the pure solvent times the mole fraction of the solvent. So this equation here, let's see what we've got. As far as the mole fraction is concerned, the moles of glucose is 0.1, 18 divided by 180. The moles of water is 10, 180 divided by 18. And so the mole fraction of water is the 10 moles of water divided by the 10.1 total moles. Mole fraction of water 0.99. Pop that into the equation. Vapor pressure, therefore, is 24 millimeters of mercury. The vapor pressure of the pure solvent multiplied by 0.99, the mole fraction of water. So the vapor pressure of this solution, just a little bit less, but the point is it's less because those solute particles are getting in the way. And indeed, it's 99% of what it would have been because 1% of the surface particles are going to be solute particles in this particular case. Had to restart, sorry, had a frog in my throat and I was messing things up. So anyway, 2 more properties that we'll look at. These are the ones that you study in the lab. Again, we're going to say volatile liquid solvent, non-volatile solute. As your solvent is liquid, liquids boil, liquids freeze, so we're going to study the boiling point and freezing point. Boiling point of a solution that has the non-volatile solute is increased compared to that of the solvent. Freezing point of the solution in which you have a non-volatile solute is decreased compared to that of the solvent. Okay, both of these have applications in everyday lives. We just had snow, and so they put salt all over the road because that salt mixes with the ice to make a salt solution which has a lower freezing point, so therefore makes the ice melt. And boiling point and freezing point are changed in your car radiator when you mix in ethylene glycol or propylene glycol. It makes a lower freezing point, so your radiator is less likely to freeze. High boiling point, so your radiator's less likely to boil. Both of these you can interpret in terms of entropy. Okay, your solution's got more entropy than the pure solvent by definition, and so that means that there's going to be less of a tendency for it to want to get more entropy to become a gas because it's already got more entropy, and it's going to be harder to freeze it because it's got more entropy. Therefore, to go down to the solid is going to require a greater influence. Change in boiling point compared to the solvent is equal to some constant times the mole fraction of the solute. So again, the concentration of the solute increases the difference in the boiling point between the solution and the solvent. Value of K here is equal to R times the boiling point squared of the pure solvent. That's what that star means, divided by the heat of vaporization of the solvent. Same idea for the freezing point. Change in freezing point is proportional to the mole fraction of the solute. Here's the constant of proportionality, which is equal to R times the freezing point of the solvent squared divided by the heat of fusion. TF is always bigger than, or KF is always bigger than KB. In other words, the effect on the freezing point is always greater than the effect of the boiling point, simply because of this difference between the heat of vaporization and the heat of fusion. Heat of vaporization is always bigger than the heat of fusion, so that means that this constant is going to be smaller for boiling than it is for the freezing. Most of the time in the lab, we don't talk about the mole fraction, we talk about the molality, which is the moles of solute over the kilograms of solvent. If you have a sufficiently dilute solution, well then in the mole fraction, you can say it's moles of solute divided by moles of solvent. And of course, if you just got moles of solvent on the bottom, then you can turn that to kilograms of solvent very, very easily. When we do this, change in boiling point equals Kb times the molality. Change in freezing point is Kf times the molality. This is the form that you see in the lab environment. Quick couple of examples for our glucose solution: 18 grams of glucose in 180 grams of water. Calculate the boiling and freezing points, give you these constants, which are constant for water, right? Any aqueous solution has these constants. Kb smaller than Kf, as I pointed out, because the heat of vaporization is bigger than the heat of fusion. Assume normal conditions. Simply by that I mean the boiling point of water is 100 Celsius and the freezing point is 0 Celsius. So anyway, molality is the moles of solute over kilograms of solvent. Where it worked out 18 grams of glucose is 0.1 moles of glucose, 180 grams, 0.18 kilograms of water. So the molality of this glucose solution, 0.556 molal. Change in boiling point is Kb, which I tell you, times the molality, which we just figured out. Pop that in. Change in boiling point, 0.284 Celsius. In other words, this solution boils at about 0.3 degrees Celsius more than the solvent, more than pure water. Water, of course, boils normally at 100, so 100 plus 0.284 is about 100.3 degrees Celsius. Same process for the freezing point, different number for the freezing point constant. So the change in freezing point is 1 degree, so in other words, bigger, as we saw, than the change in the boiling point. Freezing point of water usually 0. Freezing point is less, so we subtract this difference, and so the freezing point of this solution minus 1.03 degrees Celsius. One of the fun things historically about colligative properties is that before mass spec and so forth came along, colligative properties could be used to determine the molar mass of an unknown solid. You might remember from your treatment of gases in the ideal gas law that if you know the mass, the volume, the pressure and temperature of a gas sample, if it's a pure gas, you can determine the molar mass of the gas. That works great for gases. It works great if you have unknown liquids that you can evaporate. But what if you have unknown solids? Well, as we will discuss in this particular example, you can use freezing point depression, boiling point elevation, or for larger molecules, osmotic pressure that we'll get to later on, in order to determine the molar mass of an unknown. So looking at this, 2.3 grams of unknown solid dissolved in 80 grams of water. The resulting solution freezes at minus 0.7 degrees Celsius, so we will assume a change in freezing point of 0.7 degrees Celsius, determine the molar mass of the solid. Well, we know that the change in freezing point is the freezing point constant times the molality. In this case here, we know the freezing point constant, we know the change in freezing point. Pop those in and we can determine that our solution has a molality of 0.376. Now, molality is moles of solute divided by the kilograms of solvent. We know our molality, we just calculated it from the change in freezing point. We know we had 80 grams of water, or 0.08 kilograms of water. Thus, we can determine the number of moles of our solute to be 0.030 moles. Well, we know the mass, we know the moles, we can calculate the molar mass, which is simply the grams over the moles, the mass of a particular sample divided by the number of moles we have in it. We had 2.3 grams, 0.03 moles. Molar mass, 76.5 grams per mole. A really fun experiment to actually do in lab, although I think all of this has been removed from the A-level curriculum. More is the pity. Electrolyte solutions, you study these in lab as well. Historically, it was actually using colligative properties that Arrhenius determined that ionic substances dissociate in water. Just to give you some quick examples, if we think of 0.1 aqueous glucose, change in freezing point is 0.1 molal times 1.86 degrees Celsius per molal. So that will change about 0.2, so it freezes about minus 0.2 Celsius. Okay, so make sure here's the solution. Here's the change in freezing point to be expected for 0.1 molal solution is 0.2, and so the actual freezing point minus 0.2 Celsius. If we took ethanol, same idea, 0.1 molar will have a change of 0.2 Celsius, so a freezing point of minus 0.2 Celsius. Acetone as well, 0.1 molar acetone, same calculation, change of 0.2 degrees Celsius, an actual freezing point of minus 0.2 degrees Celsius. However, if we take 0.1 molar sodium chloride, we actually find that the freezing point of that solution is about negative 0.4 degrees Celsius. In other words, it changed by 0.4. If we take calcium chloride, we find it freezes at negative 0.6. So change of 0.6. Now notice I haven't changed concentration, they're all 0.1. And then 0.1 sodium phosphate actually freezes at minus 0.8, so that's a change of 0.8. So why do these three ionic substances have a much bigger change in the freezing point? And the answer is because, remember, the particles get in the way. Ionic substances dissociate. So sodium chloride dissociates into sodium plus and chloride. So there's two particles. Each particle effectively changes by 0.2, so the whole thing changes by 0.4. Calcium chloride, you've got three particles. Each particle changes by 0.2, so therefore 0.6 change. And then sodium phosphate, you've got four particles, change of 0.8. Electrolytic solutions have an effect that's I times greater. That's called the Van Hoff factor. Ideally, I is the number of ions into which it dissociates. So in other words, more bang for your buck with sodium because you have two particles for every sodium chloride, three particles for calcium chloride, four particles for sodium phosphate. And so the change in freezing point is not just the constant multiplied by the molality, that you also have this I in there, the extra number of particles. And of course I could have put change in freezing point there. I could have also talked about the vapor pressure change. In reality, you hardly ever see 2, 3, and 4 for sodium chloride, calcium chloride, sodium phosphate, unless it's a very dilute solution, because you run into the whole activity. Not all the sodium chlorides are dissociated at a given time, for example. Therefore, you're not going to have a 2-to-1 particle, but maybe 1.9 times, and so on. Again, done in the lab where you determine actually the I value, the Van Hoff value, for two different concentrations of sodium chloride, calcium chloride, and sodium phosphate. Very last colligative property, osmotic pressure. If you take, for example, here a U-tube in which you have a solvent on one side and a solution on the other side, and in between them you have what's called a semi-permeable membrane that allows solvent to pass through but does not allow solute particles to pass through, then what you find is that solvent particles will move through and you'll have this difference in the height in this U-tube. That difference in height you can think of as being pi, which is the osmotic pressure. Okay, pi is equal to the molarity times R times T. We got the Van Hoff factor in there as well. Okay, consider our favorite solute, glucose, but in this case let's think about 0.28 molar glucose at 37 degrees Celsius. Pi is I times MRT. Well, I for glucose is 1. Molarity 0.28, R 0.0821 liter atmospheres per mole Kelvin, temperature 37 Celsius or 310 Kelvin. Pi is 7.13 atmospheres. Okay. Another way to think about osmotic pressure, and this is actually how it's measured in the lab, is not looking at the height between them, but finding out what pressure is needed to push down on here to stop osmosis. In other words, what pressure do you have to put here to stop the solvent particles passing through? So in this case, if we put 7.13 atmospheres of pressure, what we would find is that there wouldn't be a height difference at all. That you just have the same height of solvent on both sides, but you needed that pressure of 7.13 atmospheres to stop the motion of solvent particles. I did want to have an osmometry lab in there for you. Unfortunately, nobody here that I could find does it. Maybe future years we'll have that. Anyway, very fast little excursions through colligative properties. Ideally, you're watching this before you do the lab, if you're doing the lab before the lecture, which is the case in 2018.